Hi, everyone, and welcome back to Organic Chemistry on YouTube. Today, we're going to be talking about the synthesis of aldehydes and ketones through the process known as ozonolysis. In the last video, I discussed the oxidizing reagent potassium permanganate. This was a relatively harsh reagent that over-oxidized and led to the production of carboxylic acids instead of stopping at aldehydes, for example. So ozonolysis is an oxidative cleavage reaction that acts on alkenes to form both aldehydes and ketones, depending on the actual reagent. But no carboxylic acids are formed when using ozonolysis. Two, this is known as a mild reagent and has mild reaction conditions, which generally means you don't need a lot of heating or high extreme pHs, high or low. And two, this has kind of a complicated multi-step reaction mechanism. So let's dig into that. So first of all, if we have an alkene, let's use the same reagent we've been using. This undergoes a reaction with ozone, that's O3, at very low temperatures, minus 78 Celsius, and a second step that involves DMS, and I'll introduce what DMS is in just a moment. And this will produce a ketone and formaldehyde. Okay, so in potassium permanganate, that formaldehyde would continue to be oxidized to carbon dioxide, but here we don't see that. So let's look at this mechanism. First of all, let's draw the resonance structures and Lewis structures of ozone. So here's the Lewis structure and one resonance form. We can draw another one by pushing the electrons onto the more electrophilic oxygen. Okay, and this is also known as a 1,3 dipole. So this 1,3 dipole can undergo, well, what's known as a 1,3 dipolar cycloaddition onto this alkene. I'll show you that step here. So essentially, the alkene itself, the nucleophilic pi bond, will attack this oxygen, push the electrons onto that central oxygen, and then use the lone pairs on the terminal oxygen and attack this carbon. This leads to this intermediate. Okay, and then this can spontaneously rearrange to make this compound here. Okay, so now these two can undergo a reaction themselves, and I'll draw these in different colors to make it a little easy to follow. We're going to use this nucleophilic oxygen, these electrons here. We're going to use these electrons, which I'm going to show in red as the most nucleophilic part of this, of these two molecules. And this is going to hit this electrophilic terminus of the formaldehyde. Then this pi bond will attack at the same time this really electrophilic terminus of this structure here and kick those electrons up to there. Okay, now this will end up creating a structure which makes this compound here. Recognizing that dimethyl sulfide DMS is a pretty good nucleophile will help you through the next steps. So dimethyl sulfide will attack this oxygen as the electrons from this oxygen go back and attack the sulfur. This helps to make a sulfur-oxygen bond. As this reaction happens, the oxygen-oxygen bonds, which I'm showing with these two electrons here, collapses to form will become the ketone. And this carbon, this carbon-oxygen single bond collapses to form what will become the aldehyde. And then the two electrons that are left on this carbon-oxygen bond will go back onto the oxygen, okay, to replenish the charge that gets added to the sulfur. So let's go ahead and show these compounds. So this ketone comes from this part of the compound. This aldehyde comes from this part of the compound. And one of the byproducts dimethyl sulfoxide might be familiar from chapter 6 because this is DMSO. Okay, so this is an example of the mechanism. Let's talk about a few questions you might ask in office hour. 1, why doesn't this reaction over-oxidize alkenes? 2, are there medicines that have aldehydes instead of carboxylic acids, where an ozonolysis reaction would be really helpful? And 3, would ozonolysis work at higher temperatures, given that these reaction conditions are pretty low temperature, minus 78 degrees Celsius reactions? I want to stress 5 minutes is not enough to cover ozonolysis, and you should spend much more time than that working on this mechanism and understanding this reaction. With that, this has been Organic Chemistry in 5 minutes or less. Thanks for tuning in.